Welcome you all to the 12-week open online course on digital electronics and system design. Before starting, let me give you a brief overview of the learning objectives and learning outcome for week 1 of the course. An introduction to analog and digital signal and a brief justification for the shift to digital systems, the different types of number systems and their conversion from one number system to another, the use of binary codes to represent numeric and alphanumeric data, and understanding the rules of arithmetic operations like addition, subtraction, multiplication and division in binary number system. On completion of the week 1 course module, the learners will be able to comprehend the following learning outcomes, starting with differentiate between analog, discrete and digital signals, understand the different types of number systems, perform arithmetic operation using binary number system, and use of different types of binary codes. When we say signal, it implies what? Signal is a variation in physical parameter. Our speech is a signal, the temperature, pressure variation is a signal, the speed of a moving vehicle is also a signal. Take an example. I am addressing you, an audience in a hall. My speech signal is converted to an electrical signal by the microphone, process it and is transmitted through the wires or the twisted coaxial cables to the speaker, where again my electrical signal is converted back to a sound signal. When I say processing of a signal, it generally means either the amplification or the amplification and storage, or the amplification, filtering of the signal, storage, reproduction and transmission, or all of the above process. Electronic circuits and systems are of two types, analog and digital. Analog circuits are those in which the signals vary continuously between a maximum and minimum value, that is within a fixed limit, or we call the range of the signal. The left hand side of the figure shows an analog signal. As an electronic or electrical engineer, for example, the common signal which we observe or measure is either a voltage or current signal. From the figure, it is observed that the magnitude of the signal changes at every instant of time. That is, if I take a voltage signal, it is in the positive half cycle, it is the maximum value is plus V max, and in the negative half of cycle it is minus V max, or we may say it is I max and I minimum. That is the range of the signal, but within a fixed limit or range. As seen in the figure, at one instant of time the signal value is 0, and another time instant it reaches a positive or negative peak or maximum value. Suppose I am observing the pressure of a steam boiler. I am not interested to know the pressure value at every time instant, but only at fixed interval of time. Let us take the example, the boiler steam pressure. Say at time 10 am, the pressure is 1 Pascal, and again after half an hour or 1 hour time interval, I am measuring the pressure's value and it is observed as 3 Pascal, or let us assume it as 2.75 Pascal. Accordingly, the boiler operator takes a logical decision whether to close or open the pressure valve, or a logical decision through controller for automatic valve operation. The decisions are taken based on observed measured values at discrete time instants. The right hand side figure which is shown on your screen is the discrete signal. As you see in the figure, a discrete time signal has a value specified only at discrete points in time. Here at definite time intervals, we can say it is 10 milliseconds or 10 microseconds or half an hour, the signal value is measured or observed. Our interest is to know the magnitude of the measured or observed values at specified intervals of time, then it is a discrete signal. And how it is obtained? It is obtained by some sampling continuous time signals. The question is how faithfully the discrete signal can be converted back to an analog signal. It depends on the sampling time interval. In real world applications, all signals are analog in nature. If you observe the ECG of a heart patient, one can see a pattern of waveform with varying peak values. Doctors, after monitoring these waveforms, make inference about the patient's heart condition. A discrete signal here cannot serve the purpose. Coming back to the analog signal, for example, let us take the range of a voltage signal between 0 and 5 volt, that is, its minimum value is 0 volt and its maximum value is 5 volt. Within this range, it can take any value. The only problem is representation of the measured value, that is the number of digits to make it more meaningful, whether it should be 4.756 volt or 4.7568 volt. So, theoretically one can say it can have infinite values within the given range. The question is how accurately I can transmit the signal without noise interference or measure the signal, because in analog signal the accuracy also depends on the observational power or the accuracy of the measuring instruments. If I want to store it or reproduce and transmit it, the limitation will be the number of digits to be used to represent the observed value or the channel size. The above issue can be resolved if we can discretize the amplitude also in the form of levels. The number of levels decide the accuracy of my digital circuit. As shown in the figure, let us denote as L0 be 0 volt, that is level 0, L1 from 0 to 1.25 volt, L2 between 1.25 to 2.5 volt, L3 between 2.5 to 3.75 volt, and L4 from 3.75 to 5 volt. So, there are 4 levels you can see. At the time instant t1, the level is L2. The voltage magnitude is between 1.25 volt and 2.5 volt. We can take either 1.25 volt or 2.5 volt as the observed or measured value. It is the designer who has to take the decision whether to read the observed value as 1.25 volt or 2.5 volt. Similarly, at time instant t3, the level is L4 and the measured value is 5 volt. Here also one can increase the accuracy by adding more levels. Assume the number of levels have increased from 4 to 8. Now, 0 is denoted as L0, that is 0 volt as L0, L1 lying from 0 to 0.625 volt, L2 between 0.625 volt to 1.28 volt, L3 between 1.25 to 1.875, L4 from 1.875 to 2.5, L5 from 2.5 to 3.125 volts, L6 from 3.125 to 3.75 volt, and L7 from 3.75 to 4.375 volt, and L8 from 4.375 to 5 volt. As the number of level increases, we can see that the complexity also increases. So, what we do in a digital signal, we discretize the amplitude and time, and then we call it as a digital signal. Fewer digits to represent a digital signal. So, one thing what we can do is that we can convert the analog signals to a digital signal by sampling and then by quantization. Digital signals carry binary data, that is 0 or 1 in the form of binary bits. It can only contain one value at a period of time. The binary digit 1 used to represent a high voltage level, in our case it is the 5 volt, and binary digit 0 is to represent low voltage level, and in our case it is the 0 volt. The digital signals are represented as square waves or pulses. So, let us summarize what are the advantages of a digital system. The first advantage, it is easier to design. Digital circuits or switching circuit operation depends on the voltage level, as discussed earlier, high or low. The exact numerical value of the sensed input parameters is not important as in analog circuit. The second advantage is that the data storage is easy. Digital signals or allow storage to store a wide variety of information that is often difficult to encode in analog form. For example, the text is represented quite easily with the binary ASCII code, that is a 7-bit code, or the 8-bit EBCD code, where each character including the punctuation marks, spaces and carrier returns can be easily stored. The third advantage is increased accuracy obtained by adding more switching circuits. To obtain the same accuracy in analog system requires complex hardware with increased cost. The physical restriction of the component used in analog systems like resistors, capacitors is also an issue due to the aging, temperature variation and other factors. The fourth advantage is that the digital signals are immune to noise. What is noise? Unwanted electrical signals are called noise. In digital circuit, the range of value is important, that is the voltage level, whether it is high or low, as long as the noise level is insignificant. Let us take the example of an analog signal. Suppose I am sending an analog signal of 5 volt and I am transmitting it, and a 0.3 volt has added as a noise, and at the receiving end I receive it as 5.3 volt. So, the receiver is not sure whether what the voltage level has been transmitted, whether it is 5 volt or 5.3 volt. This noise problem is not there in digital signals, because if I send, suppose my level is level 1 and it is between 0 and 1.25 volt, and between this level I am only interested in the level. Even if a noise of 0.3 is added, suppose it is 0.625 and a noise of 0.3 is added, so it is going to be 0.925, but my level has not changed. So, that is the advantage which I get in a digital signal, that is immune to noise. The fifth advantage is that it is more reliable. In digital signal, for example, out of n values, the value which is selected is determined by the sampling instant, whereas with analog signal, the observed data to be more meaningful, it has to be decided over a time frame. Then we come to the number system. The next topic is the number system. Number system relates quantities and symbols. The number system represents the value of a given number with respect to its given base. Human beings use the decimal number system for their everyday activities, whether counting or measurement. The digital system uses the binary number system. The base value of any number system determines the unique representation of a given number, and so different number systems has different representation of the same number. So, let us start with the decimal number system. The decimal number system has a base or radix 10, as it uses 10 independent symbols, that is symbols starting from digit 0, 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9 to represent a number in decimal system. The decimal number 10 is represented by the symbol 0 and 1, where symbol 0 is the least significant digit or the rightmost digit we say, and symbol 1 is the most significant digit or the leftmost digit in the decimal number 10. In general, a decimal number system with decimal points is represented as D3, D2, D1, D0 on, that is the integer part of the decimal system, and thereafter there is a decimal point, and after that the fractional part is denoted as D minus 1, D minus 2. In decimal system, each digit position represents a specific power of base 10. The rightmost digit is of the order of 10 raised to 0. We call it as the unit or ones place. The second rightmost digit is of the order 10 raised to 1, that is the tens place. The third rightmost digit is of the order of 10 raised to 2, that we call it as the hundreds place. The fourth rightmost digit thousands, and so on, that is 10 raised to 3. Similarly, the weights of the first digit after the decimal point, second digit after the decimal point are of the order 10 raised to minus 1, that is the first digit after the decimal point, and the second digit after the decimal point, the power is 10 raised to minus 2, that is 1 by 100, and so on. The decimal digit represented by coefficient dk, that means that where k is the subscript, represents any of the decimal digits from 0 to 9, and the subscript k indicates the position value and hence the power of base, that is base 10, to which the coefficient must be applied. For the decimal number system as shown, it will be as follows: d, and the subscript k is 3 into 10 raised to 3, where 10 raised to 3 shows the positional weight, plus d2 into 10 raised to 2, that is the positional weight, plus d1 into 10 raised to 1, that is the positional weight, that is the tens place, plus d0 into 10 raised to 0, that is the unit place or the ones place. This is the integer part of the decimal number system. So, after the decimal point, coming to the fractional part, starting from the rightmost decimal digit, we have d raised to with the subscript minus 1, indicating its power is 10 raised to minus 1, that is 1 by 10, plus d with the subscript minus 2 into 10 raised to minus 2, that is the position or its weight is 1 by 100. Now we come to the binary number system. The binary system has two independent symbols, namely 0 and 1. Therefore, the base or radix is 2. A binary digit is also called a bit. The binary system is again a positional weight system, where each bit represents a specific power of base 2. The rightmost bit of a binary system is called the least significant bit, and the leftmost bit is called the most significant bit. A binary number system with binary point, because we are dealing with binary number system where we replace the decimal point, now we call it as binary point, is represented as B3, B2, B1, B0, that is the integer part of the binary system, and the fractional part after the binary point, that is B minus 1, B minus 2. The binary bit represented by coefficient Bk represents either bit 0 or bit 1, and the subscript k indicates the position value and hence the power of base, that is base 2, to which the coefficient must be applied. So, we have an example here, the binary numbers as shown. We can say that B3 into the position of that binary bit, that is 2 raised to 3, plus B2 into 2 raised to 2, plus B1 into 2 raised to 1, plus B0 into 2 raised to 0, and that is the integer part of the binary number system. And after the binary bit point, on the rightmost binary bit, b raised to minus 1 into 2 raised to minus 1, that is the positional power, that is 1 by 2, plus b raised to minus 2 into 2 raised to minus 2. If you got a third bit, we call it as plus b minus 3 into 2 raised to minus 3. Now we come to the octal number system. The octal number system was used by early macrocomputers. In octal number system, there are 8 independent symbols starting from 0, 1, 2, 3, 4, 5, 6 and 7. Therefore, we say the base or the radix is 8. The octal number system is also a positional number system, wherein each digit of the octal system represents a specific power of base 8. So we have an example here. I am denoting it as O2 with subscript, the k is 2 and its positional power is 8 raised to 2 or 64 plus O1 into 8 raised to 1 or 8 plus O0 into 8 raised to 0 plus after the octal point we say O minus 1 with a position 8 raised to minus 1, that is 1 by 8 plus O minus 2 into 8 raised to minus 2, that is position is 1 by 64. Then we come to the next part of the number system, that is the hexadecimal number system, the most popular number system for data processing in digital system. Here the independent symbols used are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then A to represent the decimal number 10, B to represent the decimal number 11, C to represent the decimal number 12, D the decimal number 13, E the decimal number 14 and F the decimal number 15. So we have got 16 symbols and therefore the base or radix we say it as 16. The hexadecimal number system is also a positional number system wherein each digit of the hexadecimal number system represents a specific power of base 16. So we have an example over here, starting with the most significant bit or the most significant number of the hexadecimal system S3 with its position 16 raised to 3, the positional power, plus S2 into 16 raised to 2 plus H1 into 16 raised to 1 plus H0 into 16 raised to 0 plus, if we come after the hexadecimal point, we have got H with the subscript minus 1 into 16 raised to minus 1 plus H minus 2 into 16 raised to minus 2. So now we come to the number system conversion. So from the figure we can say that the decimal number system can be converted directly to binary, it can be converted directly to octal, it can be converted directly to hexadecimal, or from hexadecimal back to decimal, from binary back to decimal. So that means all the conversion system can take place on both ways. We will start first with the decimal to binary conversion. The integer part of the decimal number system is successively divided by the base of the number system to which conversion is to be done till the quotient is 0 to get the binary integer. The last remainder will be the most significant bit. Now let us take an example. Convert the decimal number 40.875 to binary. So we have to successively divide it by 2 as shown in the table. So I first divide my decimal number, that is the integer part, I take the integer part, divide it by 2, so it comes to 20 and the remainder is 0. Then again I divide 20 by 2, so we get 10 and the remainder is 0. Again I divide it by 2, we get 5 and the remainder is 0. Again I divide it by 2, 2 2s are 4, the remainder is 1. And again I divided 2, so I get 2 1s are 2 and the remainder is 0. So if we start with the most significant bit, my binary number of the integer part of the decimal number, that is 40, is 101000. Now comes to the fractional part. The fractional part of the decimal number, if any, has to be successfully multiplied by decimal number 2. Here we are multiplying, not dividing, till the 0 is obtained after the decimal point or till the requisite number of bits has been obtained. So we have got the example, the fractional part, that is 0.875. So what we are doing, we first multiply it by 2, so we get it as 1.75. So we have got the integer part, that is 1, and we then again multiply the fractional part, that is 0.75 by 2. Now we get 1.50. So we are leaving the integer part and the fractional part is 0.50. So again we are multiplying it by 2, so we get 1.00. That means there is no fractional part. So we have got 111. To read the integers in the forward direction, we get the result as 0.111. So now we combine the integer and fractional part of the converted number system, and the binary equivalent of the decimal number is 101,000.111. Now we convert a binary number to a decimal number. Binary numbers are converted to decimal number by their positional weight system. Each binary bit of the binary number system is multiplied by the corresponding positional weight. The result of each product terms are then added to obtain the decimal number. So we have got, for an example, I have to convert a binary number 1101.11 to the decimal numbers. So starting from 1, we can convert 1 into 2 raised to what is the position? 1 into 2 raised to cube, that is the positional weight, plus 0 into 2 square, plus 0 into 2 raised to 1, plus 1 into 2 raised to 0. Now we come to the fractional part. The fractional part we have got, that is 0.11. So we convert 1 into 2 raised to 1 plus 1 into 2 raised to minus 2. Now the product which we obtained, that is 1 into 2 cube, that is 8, then plus 0 into 2 square, that is 0, plus 0 into 2 raised to 1, again 0, plus 1 into 2 raised to 0, that is 1, and after the binary point 1 into 2 raised to minus 1, that is 1 by 2, 0.5, plus 1 into 2 raised to minus 2, that is 1 by 4, that is 0.5 plus 0.25, and we add all this, we get the decimal number 9.75. Now we come to the next conversion system, that is decimal to octal. The base of the octal number system, as you all know, is 8. So now we have to successfully divide the integer part of the decimal number system by the base, that is 8, till the quotient becomes 0. For conversion of the fractional part, convert the fractional part of the decimal number system by successively multiplying it by 8 and keep noting the integer part. Repeat till 0 is obtained after the decimal point or till the desired result or accuracy is obtained. Now I have to convert my decimal number system, that is 360.93 to octal number. Now we are converting first the integer part of the decimal number system, that is 360. So we have to successively divide it by the base of the octal number system, that is 8. So first we divide 360 by 8, we get 45 with remainder as 0. Then again we divide 45 by 8, 8 5s are 40 with your remainder as 5, and then the final, the quotient which is remaining, that is 5, it becomes the most significant bit. So now the fractional part we have to convert. So how you convert the fractional part? We have to successively multiply by 8 and keep noting the integer part as shown here. So we first convert the fractional part, multiply it by 8, you get 7.44. We keep the integer, that is 7. Then the fractional part again we multiply, that is 0.44 into 8. We get 3.52. We keep the integer as 3, and again we multiply the fractional part, we get 4.16. We keep the integer as 4. So now we read the integer in the forward direction, the result is 0.734. So as we had done earlier in decimal to binary conversion system, combine the integer and fractional part of the converted number system. So we get the equivalent as 550.734. That is the equivalent of the decimal number, that is 360.93 as 550.734 in octal number system. Hope you had a good learning experience watching this video. Thank you and see you all in the next lecture. Once again, thanks.